What we have been looking at is to see what is the contribution of the intensity, what is the contribution towards the intensity once atoms are found in some positions. For example, in the case of cesium chloride, we discussed the issue that cesium is at 0, 0, 0, chlorine is at half, 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 and then we calculated the intensities associated with various reflections like I100, I200 and so on. We found that in all these expressions the intensity gets simplified, mainly because of the fact that cesium is sitting at the origin, which makes cesium to be at 0, 0, 0, and chlorine is sitting at half, half, half. So, it makes it contribute to various planes depending on its location. So, remember we have to use the expression capital D HKL by small d HKL. That is the one which gives us the ratio of how the position of the atom is with respect to the given plane. For example, if you take 210 here, the chlorine atom is positioned exactly midway between the parallel planes which pass through this point defining 210, and this is again 210. So, these are parallel planes. So, this was a methodology with which we developed that the intensities can be calculated, and we indeed calculated several intensities. But in a general case, it is not always cesium chloride we are worried about. We are worried about hundreds of atoms, and these hundreds of atoms by symmetry are generating, let us say, more than 4 or 5 molecules in the unit cell. So, it is a very large assembly of atoms, and each and every atom now from our discussion contributes to a given plane. The interference issues with waves coming out of these atomic positions, because it is the electrons which scatter X-rays. So, depending on the electron density we get contribution to various planes, and these are now constructively or destructively interfering, and therefore, the intensity associated with a plane gets calculated. The issue is now how can we get a general expression, because we can't just every time go and find out where the atoms are sitting and then calculate. Instead, there should be a very general expression depending upon wherever the atom is sitting in the unit cell, we should be able to calculate the contribution to the plane. And that is the idea with which we will now develop a general expression, as I have written here, a general expression for the calculation of intensities. This will be applicable to all 3 dimensions, and therefore, it is in a unit cell. Depending upon where the positioning of the plane is, we should be able to calculate the contribution to that plane from all the atoms that are present in the unit cell. So, this is therefore a very important calculation, which will sort of generalize how we approach the various issues of how to calculate the intensity. So, what we will do is we will first derive the general expression and then incorporate the general expression for finding the contribution to various planes, the intensity contribution from the presence of hundreds of atoms or thousands of atoms or whatever it is. So, this in principle is easily programmable. So, we can develop packages with which we can calculate intensities. Whenever I am saying calculating intensities, it means that we already know the positions of the atoms. So, it is only after the structure is determined we can calculate intensities, that we must remember. So, that means we should know the positions of the atoms before we calculate intensities. But the general expression for calculating intensity will always be automatically coming, and that is obtained by this diagram in which I show a 2-dimensional projection, x along this direction and y along this direction. This is the angle between x and y, and of course, z is coming in a direction away from the plane of the projection. So, if you consider a plane passing through the origin, as we have always discussed, this particular plane will have a phase difference of 0, because there is no path difference at 0, 0, 0. We also have shown that all atoms lying on this plane will scatter in the same phase. So, the phase is 0 associated with atoms lying in that plane. What then we will do is to take, by definition of the Bragg's law, we take the first plane which comes out of this particular 0, 0, 0 position, and let us take a general position where we will have the first position coming, which is shown here. This is the first plane out of it. That means the phase change will be 2 pi. So, whenever the phase change is 2 pi, we have the lambda as the path difference, and therefore, we satisfy the condition 2 d HKL, 2 sin theta, sin 2 d sin theta equals lambda. So, we satisfy that expression, which is the Bragg's expression. So, suppose we have an atom at x 0 0 along the direction of x. We locate an atom x 0 0. The contribution of this atom to this plane, we know already how to calculate. What we do is we draw a line parallel to this plane passing through the x 0 0 like that, and then we calculate the distance of this particular plane from the origin, and then we take the a by h, of course, a by h, b by k and c by l will be the intersections for the first given plane. So, depending upon what is the value of h, k and l, we can define this particular plane. So, the first plane which obeys the Bragg equation will come at a distance of a divided by h, where a is the unit cell, h is the Miller index, b by k, where k is the Miller index, b is the unit cell, and of course, in the third direction it will be c by l. So, if we now consider this as the x 0 0, then what is the phase that is associated with this, because that is what we want to calculate the intensity. So, the first HKL plane out from the origin makes an intercept a divided by h, which is what we have shown here, with a phase change of 2 pi. So, the first phase change is 2 pi. Atom is at x 0 0. So, what would be the d, capital D by small d HKL? The capital D is 2 pi a into x, because that is the distance which up to that x 0 0 point, 2 pi a into x divided by a by h, which is the value here. So, if we take this 2 by a x divided by a by h, this will give rise to 2 pi h x. So, 2 pi h x is now the plane, the phase that is associated with this particular atom, its contribution to the plane, which is the first plane out of 0 0 0. So, the contribution to this plane is 2 pi h x if there is a atom sitting at x 0 0. Likewise, if there is an atom sitting at 0 y 0, it will become 2 pi k y, because it will be 2 pi b into y divided by b by k. So, that will become therefore 2 pi k into y, and similarly if it is in the L direction, it will become 2 pi L into z. So, in the case where the atom is sitting at x y 0, let us say we have an atom here. So, what we have to do is to draw a line parallel to that, calculate the capital D HKL, and the small d HKL is already available, and therefore, that will be the atom is at x y 0. So, the corresponding phase will be 2 pi times h x plus k y, h x due to this direction, k y due to that direction, and therefore, we have x contribution, y contribution both taken into account. So, the phase change will be phi equals 2 pi h x plus k y. So, this diagram therefore is a general picture of any crystal structure which will have this kind of disposition. We have considered the positions of 3 different atoms corresponding to their contributions to this particular plane, and the phase changes have been calculated. Once we have the phase changes, we can always calculate the intensity that is associated with it, because an atom in a general position x y z will give rise to a phase change of 2 pi h x plus k y plus L z, and of course, the amplitude will be proportional to that of f, which is the atomic scattering factor corresponding to the scattering angle theta, about which the reciprocal lattice vector is located. So, what is important here is the location of the reciprocal lattice point. The location of the reciprocal point is this, associated with the plane, and the amplitude therefore has to be read proportional to that. So, whatever is the value of f at that particular corresponding scattering angle, which is corresponding sin theta by lambda, has to be read out, and then we substitute it to calculate the intensity. This is something which we will now consider and see whether we can do this in very simple terms. Let us take a unit cell with n atoms. So, now we have a unit cell with n atoms, we have various planes passing through this crystal, it is any general crystal. So, the cell dimensions are A, B, C, alpha, beta, gamma. So, in such situations what we have is we have a variety of atoms in our structure. So, let us say we have n type of atoms at n different positions, a very general discussion. So, the atomic scattering factors are F1, F2, F3 so on, and the coordinates are x1, y1, z1, x2, y2, z2, x3, y3, z3 and so on. So, if there are n atoms we have therefore the Fn corresponding to the atomic scattering factor nth atom and xn, yn, zn as the coordinates. Then we write the expression for I of HKL. Now, remember the I of HKL expression we should contain contributions from every one of these items, and therefore, we have F1 cosine 2 pi. Now, this is the phase change, we have already calculated the phase change to be 2 pi times Hx plus Ky plus Lz. Now, the atom is at x1, y1, z1. So, we get this first term as F1 cosine 2 pi Hx1 plus Ky1 plus Lz1 plus etc. for second, third, fourth atom until the nth atom Fn cosine 2 pi Hxn, Kyn, Lzn whole square. Notice that it has to be whole square. This is the cosine term. We will also have the sine term, because we know our wave is a complex number. We will come to the discussion of structure factors in a later time, a few maybe in about an hour and a half of discussions on this. So, what we therefore see here is the intensity consists of cosine functions and the corresponding sine functions, cosine function square plus the plus here the sine function square. So, this is the intensity associated with any HKL. So, what is the job we have at hand? We have a crystal, we have done the diffraction experiment, and we want to now calculate the contributions of atoms lying at various positions x1, y1, z1, x2, y2, z2 and so on to the overall intensity that is developing at a given plane HKL. So, for any given general plane it should be possible to calculate the contribution for coming from various atoms. So, there are n atoms here. So, all the n atoms are summed up here in this contribution. So, this can of course be written as equal to sum over 1 to n f of n cosine 2 pi Hxn plus Kyn plus Lzn whole square plus sum over 1 to n Fn sine of 2 pi the corresponding sine term square. Let us take the example of our cesium chloride again to verify whether we are doing it correctly, whether we are doing this calculation or whether this particular expression, which is a general expression for any crystal with n atoms and its contribution to any HKL plane. So, therefore, I call it as the general expression for calculating the intensities. So, we take the case of cesium chloride. Cesium is at 0, 0, 0, chlorine is at half, half, half. So, what all we have to do is to substitute the values here. So, f of Cs, the atomic scattering factor of cesium, cosine times 2 pi h into 0, k into 0, l into 0, because 0, 0, 0 is the position of x1, y1, z1. Then f of chlorine cosine 2 pi h into half, k into half, l into half whole square, and of course, the corresponding sine terms. What happens in this situation is that the sine terms will vanish. We will in fact make a general discussion of why sine terms vanish in situations where which are similar to the structure of cesium chloride. In fact, sine terms generally vanish in case you have a centrosymmetric crystal. So, if there is a inversion center in the crystal and that inversion center coincides with the origin, then all the centrosymmetric structures therefore will not have any contribution from the sine terms. On the other hand, the cosine terms do contribute in the following way. For example, the f of Cs, since it is at 0, 0, 0, there is no phase change. So, f of Cs remains as such. So, f of Cl now gets modified with this change in the phase, and the change in the phase happens to be cosine 2 pi h plus k plus l divided by 2 whole square. So, this is a general expression for deriving the intensity in case of the cesium chloride. So, all possible HKL planes which come out from the cesium chloride diffraction experiments can be calculated, and this particular value is now an absolute value because we are reading out the corresponding atomic scattering contributions from individual atoms, chlorine and cesium. So, once we take an example here, we want to calculate the intensity of some plane 420. So, what all you have to do is to substitute that expression in this expression the values. So, you take the f of Cs corresponding to that value in our f versus sin theta by lambda picture. So, we cannot take the z value, we have to take that value of f of Cs which corresponds to the scattering angle. So, if scattering angle is theta, the corresponding sin theta by lambda value has to be read for the f of Cs. Similarly for f of Cl. So, once we have those values fitted in, then the cosine value of 2 pi, now h plus k plus L here is 6. So, 6 divided by 2. So, 6 divided by 2 happens to be 3 times. So, it is essentially it so happens that it turns out to be a factor of cosine of 2 pi. So, the sine becomes plus. So, you will have f of Cs plus f of Cl square. So, for any given I of HKL you can calculate again for 100, 200, whatever contributions will come from any general HKL plane. So, those HKL planes which will contribute to this to the intensity can all be calculated. So, if we now do an experiment, let us say with cesium chloride, either a powder diffraction experiment or a single crystal experiment, let us take the case of a powder diffraction experiment, then we will get a powder pattern corresponding to cesium chloride. And that particular powder pattern will be, we will be able to index it in terms of where the HKL planes are coming by looking at the x axis of the X-ray plot. Let me show you that plot. So, let us say this is the XRD pattern, this is in fact the simulated XRD pattern using the coordinates of cesium chloride. We have calculated what are all the contributions to the to individual reflections. Since it is a powder pattern, you will see the lines. In fact, in a typical recorded powder pattern, each line will have a certain width. We will discuss those issues later when we do powder diffraction. But for our discussion now, each of these end points will represent our lattice points if it is a single crystal. So, in principle at various values of these 2 theta values, you will find the reflections appearing, and those appearance of reflections will have this amount of intensity. So, this is the arbitrary intensity because this is done on some equipment, whether you do it in an equipment in Bangalore or some other place or your place, wherever you want to go and do the experiment, the intensities will change depending upon the intensity scale will change depending upon which instrument you are using, what are the experimental conditions that are available and so on. So, this is actually a relative intensity, and this has to be scaled and brought onto the actual intensity, the absolute intensity which we get from our calculation, because in the calculation we are using the f of Cs, f of Cl as they should be at that scattering angle, and therefore, we get the absolute value. We will not worry about that aspect. What we worry about this aspect is the following, and what we should know about any powder diffraction, we will, when we do it in detail later, we will also see that, is that the geometry that is associated with the diffraction, that is the dimensions of cesium chloride, the nature of cesium chloride, the appearance and disappearance of these peaks in case of cesium chloride, all that will be indicative in the x direction. So, x direction therefore gives you the geometry of the diffraction. The x direction is the place where you can actually see the presence of 2D sin theta n lambda reflections which are satisfied. So, you do not get a continuous pattern here, you get discrete patterns. Whenever there is Bragg's law obeyed, we will get the diffraction, and that diffraction, whether it is constructive or destructive, is decided by the positions of the atoms with respect to the planes from which we are doing this locating the measurements. So, we therefore have all the planes which are coming out in the x direction. So, the x axis represents the geometry of our diffraction condition, the y axis represents the intensity that is associated with the diffraction measurement. So, because of this, we see that the associated corresponding intensities will come with respect to the individual calculations which we did for I100, I200 and so on. We calculated those intensities. So, they will come because of the fact that cesium is at 000, chlorine is at half. So, this discussion therefore assumes that we know the structure. This discussion also tells us that the way in which an XRD pattern can appear, because the XRD pattern will appear as a relative intensity versus 2 theta in all experiments which you perform in a normal diffractometer. And therefore, the 2 theta degrees which we plot in the x axis, the values associated with the x axis will therefore represent various 2 theta values. Now, these 2 theta values are the ones which will tell us what are the d values correspondingly, because we use the formula 2d sin theta equals lambda, where lambda is the wavelength we have used. So, obviously, this pattern will be different for different wavelengths. Suppose we use copper radiation, it will have this pattern. If we use molybdenum radiation, the pattern will be different. The theta values will come at different positions. So, you should remember that. But if you plot, let us say, the relative intensity against the d value, d is already incorporating the corresponding sin theta expression and so on, then the two patterns will be similar. And this is something which you must remember. So, when what is plotted along the x axis is important. But basically what is given in the x axis direction in this plot is the value that is associated with the geometry. So, the geometry of the diffraction condition we can determine. That means we can determine the unit cell, the dimensions, we can determine therefore the crystal system, we can determine where the diffraction spots are coming, and therefore the geometry of the diffraction. So, entire geometry of the diffraction is conserved along the axis, along the x axis. So, that way we know when we do a xy plot of this kind that all information on the geometry is here, all information about the structure is along the y direction, because the intensity is the one which is telling us which atom is where, and therefore the electron density distribution is covered along the y axis. So, the information that is present along the y axis therefore incidentally tells us about the way in which atoms are distributed inside the unit cell. So, obviously, the appearance of these relative intensities depend upon the symmetry associated with the material, and therefore, when we have found out the space group and the unit cell dimensions, the number of molecules in the unit cell, etc., about which we are already reasonable experts. So, this will now tell us how that contributes to the intensity measurements. So, this tells us that these are the possible reflections associated with cesium and chlorine, and A is equal to 4.123. And this is the calculated values which we get for sin theta by lambda based on the presence of where the d values are, and therefore, we can calculate based on our general expression which we derived just now. This general expression will tell us how to go about determining the intensities for any given X-ray diffraction pattern. So, this is a key equation. Now, if we take the square root of this intensity of HKL, we will get what is known as the structure factor. It is the modulus of the structure factor. We will now take up a discussion on the structure factor, but I thought that before we go into the detail of the structure factors associated with any diffraction condition, which essentially is an important factor, because you remember we had two expressions. We called them Fourier transforms of each other. We showed that f of HKL or f of r at that time, f of HKL is related by a Fourier transform to rho of r, where rho of r is the electron density, and vice versa. That is, if we from rho of r we can get to the f of r. So, those two equations are the major fundamental equations which we need in order to solve the structure. So, for example, if we know the structure factors, we can determine the structure in principle, and if we know the electron density, we can determine the structure factors. So, these Fourier transform equations tell us clearly that when we do a structure determination protocol, the structure determination in order to determine where the electron density is should have structure factors, not the intensities. So, here what we have done is to show the general equation by means of which we can calculate the intensities, because that is what we experimentally measure in a diffraction experiment. So, since we have the intensities that is available with us, we can use these intensities and then determine the structure factors. The major problem which comes up there is the phase problem. We get the magnitude of f of HKL, we do not get the alpha associated with HKL. See here, how did we solve the phase problem in calculating the intensities? We solved the phase problem by looking at the fact that if depending upon where these atoms are, the variation is with respect to 2 pi times Hx plus Ky plus Lz. So, that gave us the phase issue. This is because we know where XYZ is. Since we do not know where XYZ is, the modulus value which we get for structure factor is devoid of phases. No experimental way is available with the way we do the experiment. No experimental approach can be developed to find the phase. So, therefore, we have to determine the phases or guess the phases that are associated with the structure factors. So, you might ask a question, why not use the intensities and do a Fourier transform? What happens if we do the Fourier transform of intensities? If we do the Fourier transform of intensity, we will get what is known as a Patterson function. We will be discussing details of the Patterson function, because that is also an extraordinarily useful function, provided we know certain things about the structure. See, the intensity of HKL gives rise to the so called Patterson function, and that Patterson function is one in which we get the interatomic distances as vectors. So, it is a vector map, and in that vector map we get interatomic distances. So, in other words, what we will get if we do the Patterson of a cesium chloride example we have taken here is not the positions of the atoms, but the position of the end vectors between cesium and chlorine. We not only get the position of the vector between cesium and chlorine, we will also get vectors associated with cesium and cesium itself, chlorine and chlorine itself, chlorine to cesium, and then all the other equivalent points which get generated in this space group and their vectors. So, if there are n atoms, we will get n square vectors, out of which n will be self vectors. So, the total number of independent vectors will be n square minus n. It is very easy in case of the cesium chloride to guess what should be the Patterson map, because there are only 2 atoms in the unit cell. On the other hand, if there are hundreds of atoms, we will get an n square minus n if 100 atoms are there. So, we will get n square minus n peaks, and all these peaks will originate from the same origin. And therefore, Patterson is also a very useful tool, because we do not have the phase problem there to solve. However, the tool that can be used there is to sort of extract information from the vector map. Since there is a large number of vectors coming from a single origin, it becomes a severe overlap between vectors, and structure solution is not very straightforward. It can be done, but it is not a straightforward methodology. So, the generally recommended methodology is to measure the intensities, identify the magnitude of the structure factors by taking the square root of the intensity, and then solve the phase problem to get to the structure. So, this now is the general methodology that is available for the structure determination. So, what have we done so far? What we have done so far in terms of the structure determination, in fact, we did not determine the structure, we assumed the structure of cesium chloride, and then did the substitution of various types to get to the intensity calculations. We in fact got the absolute intensities, because we have used the realistic atoms inside the unit cell. The idea of this particular calculation was to show that we can get to the intensities given the positions of the atoms. So, even if you have thousands of positions, you can write a computer program which will use this general formula for calculating the structure factor, the intensity, and it will calculate all possible intensities. So, there is an advantage since we have fast speed computers and so on. Once we know the positions of the atoms, we can calculate all possible intensities that come out from the experiment. But that is not our motive. Our motive is to find out the positions of the atoms. So, we have now got ourselves into a situation where if we do not have the positions of the atoms, we cannot get to the intensities. So, that is something which we do not want to face. But we do get the intensities from the experiment. You see, we have an experiment. We performed an experiment. We sent a beam of X-rays onto the crystal did the diffraction. We know the geometry of the diffraction because it obeys the Bragg's conditions. We know where the particular peak has to come with respect to the 2 theta axis of the powder pattern. We have a relative intensity measured, so eventually we should find out a way in which we can put these relative intensities to absolute scale. All that is possible, but will it lead to the structure determination is a question which is going to be very difficult to answer. Very simple structures can be determined, But as we go to higher complexities, if we go to large organic molecules, inorganic coordinate systems, morphs, and then eventually to proteins and viruses, it looks an arduous task. So the task is cut out here for us to use the intensities and use the information about the geometry which we have derived from the Bragg's law conditions, and use these two aspects to find out the structure, find out where the atoms are. The challenge lies there. So the rest of the structure determination protocol which we are going to develop will depend upon how we develop this whole theoretical approach to find out the positions of the atoms. What is the plus point? The plus point is that we have done an experiment on with the X-ray diffraction techniques. So we have the machine, we generate the X-rays. I spent a little time on how we generate the X-rays, but maybe we will assume that we have the X-rays coming in because of the number of classes limited in this course. Suppose some time is available with the TAs, they may discuss how X-rays are generated. So the X-rays will be generated, they will fall onto the crystal. The crystal now diffracts and the intensities are measured. The positions of where the peaks come, the points come, now can be indexed in terms of the HKL values, because we know the scattering is now giving us the reciprocal lattice. So we use the HKL values. Using the collection of HKL values, we determine the geometry of the diffraction. So we now know what is the crystal system and what is the various ways in which we can now attempt to determine the space group, using the information that is available on the reciprocal lattice. So that will be the next aspect. How are we going to use this information to find what is the space group that is available for us to handle? And then we will know, once we know the space group, we know how many molecules are there in the unit cell, because we eventually have to solve for only one molecule. The other molecules in the unit cell can be generated by equivalent points, which we know very well. So this in a nutshell is what we will have to be doing, and therefore two things are important. One is the accuracy that is associated with indexing procedure. So if you go wrong in that, everything will go wrong. That is the first thing, that indexing procedure therefore will tell us where the HKL planes are coming, and in what way those HKL planes help us in understanding the geometry of the diffraction. Once we have that handled, then we can look at the intensities, handle the intensities by taking their square root and going over to the structure factor, the magnitude of the structure factor, guess the phases, and then go and compute the electron density using the Fourier transform expression. That will give us the final structure which we are looking for. So what then we will do is, there is one issue which I always wanted to discuss before we go further, and that is something which we have been looking at earlier in the earlier classes, the concept of reciprocal lattice. Since we have been now saying that there are two lattices, the direct lattice and the reciprocal lattice, we have also formulated the relationship between the direct lattice and the reciprocal lattice. But I think we should have a relook at this reciprocal lattice concept a little more closely, so that we now are able to see how diffraction is occurring and how we can get an access to the reciprocal lattice geometry, by means of which we can index the pattern, and then the distribution of the intensities to individual reflections. Has it got any information regarding the space group information? Can we derive a space group by looking at the intensities which have come in our three-dimensional reciprocal lattice? Because the main direct lattice has this information. So can we get that information out of our reciprocal lattice? So we now go over to that region. So before we go over to the region where we now look at what is the information the reciprocal lattice can give with respect to the space group determination, and in what way we measure the intensities and how we put them on the relative scale. All these aspects now are automatically done on diffractometers. I always keep telling all the time that crystallographers are their own enemies. That is because they have made it so very simple. Now a chemist or any other person who wants to determine a crystal, what all he has to do is put the crystal on the machine and wait for some time, and maybe a few hours nowadays, in order to get to the final structure, by just sitting at the keyboard and pressing enter buttons whenever it is asked for. So effectively the thing is, that we do get information regarding the structure without knowing any of the background we have here, and that is where the interpretation of the determined structures becomes a challenge to chemists, to physicists, to engineers and so on. And that is very important, because once we have the structure information available, it is always related to the property the material exhibits. So, the next step therefore will be to see what information we can get from the reciprocal lattice analysis. So, we will go into the details of the reciprocal lattice as we go further.